All right, in this lesson, we are going to talk about the inverse relationship between exponential and log functions. And so for each one, we are going to do it both algebraically and graphically. And so we're going to start with this exponential function. I recognize that it is exponential because my variable is in the exponent. I have a base of 2, and I have some transformations that say right 1 and up 4. Okay, and so for exponential functions, we know it has a horizontal asymptote. And so I'm going to go ahead and graph the horizontal asymptote up 4. It's usually at 0, but if we shift the graph up 4, the horizontal asymptote will be at y equals 4. Okay, and so the y-intercept is usually 1 away, and then your next good point is 2 away. But we have moved right 1. So instead of being on the y-axis, it is going to be right 1. And then my next point is going to be the base away, and then my next point is going to be the base squared away. And so distance of 4, distance of 2, distance of 1. And so this function is growing to the right and approaching the asymptote as we go to the left. Okay, and so my first critical point is usually the y-intercept. We keep track of where that is going. And so my first critical point is now at 1, 5. Okay, the asymptote is at y equals 4. The domain of exponential is always all real numbers. And the range is everything greater than the asymptote because it is above the asymptote at 4. Okay, and so for my 3 points, I have 1, 5. And then I have the point 2, 6. And then I have the point 3, 8. Okay, so for my inverse function, we just switch those to be able to create the graph. And then we can put them back on the graph. And so I have 5, 1, 6, 2, and 8, 3. Okay, so this function is going up towards the right, kind of like square root. But then instead of a horizontal asymptote, we are going to have a vertical asymptote at the x equals 4. And so now this function is going down towards the asymptote. Okay, and so for our inverse function, we can see that our first critical point is 5, 1. The asymptote is at x equals 4. The domain is everything to the right of the asymptote at 4. And then the range, it's going up forever, and it's also going down forever, so all real numbers. And so we can recognize this log function as being moved right 4. And then also shifted, usually he has an x-intercept that's 1 away, but now our 1 away point has been shifted up 1, right 4 up 1, and we see that it's a base of 2, because we have our 1 away point, our 2 away point, our 1 away point, our 2 away point, our 4. We're always measuring from the asymptote. And so to write this function, we know it's base 2, and then right 4, and then up 1. So that's if we were doing it graphically, but I also want to remind you how to do this algebraically. And so when you do it algebraically, you put y in for f of x. It's the same thing, just a different notation. And then you switch the x and y variable, just like you did with the points. but then you have to re-isolate the function, re-isolate the y. So here's y up in the exponent. And so our first step is to isolate the exponential expression. And so I need to subtract 4 from both sides, which would give me x minus 4, 2 to the y minus 1. Now that I've isolated, I have a base, I have an exponent, and I have an answer. That tells me I'm ready to convert. It's base 2 of x minus 4 equals y minus 1. So log base 2 of the x minus 4 equals y minus 1. The only way to get something out of the exponent is to convert it to logarithmic form. Okay, and then my last step is just to add 1 to both sides. It's going to stay outside the log. And so that leaves me with y equals log base 2 of x minus 4 plus 1, which is exactly what we got algebraically. Okay, and so the transformations for f of x were write 1 up 4. Write 1 up 4. That's what we found from the very beginning. And then the transformations that I wrote here for the inverse was write 4 up 1. Okay, and so the last question says, does there appear to be a reflection across y equals x? That should always be true. And so when I graph the y equals x line, you can see there is a reflection. These are mirror images across that slanted line. So for this next example, I am going to start by just finding the inverse algebraically. So I switch the x and the y, and then we have to re-isolate y, which means I need to isolate this exponential expression. And so my first step is to add the 3, since it is not part of the exponential expression. Now I'm ready to convert 2 to the x, log base 2 of x plus 3 equals the y plus 1. So now my last step is to just subtract the 1. And so that gives me y equals log base 2 of x plus 3 minus 1. And so my inverse function is log base 2 of x plus 3 minus 1. So a good way to check your work is notice I'm starting with an exponential base 2. I'm ending with a log base 2. Notice I have a plus 1 in the exponent, and I have a minus 1 outside. And then I have a minus 3 outside the exponent, and then I have a plus 3. And so they change from inside to outside and outside to inside, and their signs also change. And so that's a quick way just to check to make sure you have the right equation. Okay, and so now to graph these, we're going to use our transformation. So looking at my original function, it's base 2 shifted left 1, down 3. Okay, so for exponential functions, you always start with the horizontal asymptote, and then your 1 away point is on the y-axis unless it's been shifted left or right. In this case, it's shifted left 1. Okay, my next point is going to be the base of 2, and then my next point is going to be 4, base squared. Okay, and so there's my exponential function. That's f of x. Now for log functions, looking at this transformation, we have a left 3 and a down 1. Left 3, down 1. And so the first thing we want to graph is the vertical asymptote, which is x equals -3 now, because it's been moved left 3. And then my 1 away point is usually the x-intercept, but we have shifted it down 1. Okay, and then my next point would be 2 from the asymptote, and then my next point would be 4 from the asymptote. And so up to the right, and then down towards the asymptote. Okay, and so just verifying the graph, see if I can get rid of some of these extra lines. If I draw my y equals x line, you can see that these are reflections across the y equals x line. And so the answer to that question is yes. We've already written our transformation, so left 3, down 1. And then for the original function, it was left 1, down 3. And so for our critical points, or some significant points, starting with the blue exponential function, I have -1, -2. And then I have the point 0, -1. And then I have the point 1, 1. Looking at the red graph, my log graph, I have -2, -1, right here, -2, -1. And then I have the point 0, or 1, -1, 0, and then 1, 1. And so again, you can see that the points are just switched, x and y are switched. And so for my first critical point, -1, -2. For my inverse, it was flipped, -2, -1. For the exponential function, the asymptote was down at y equals -3. For my inverse, it was shifted left to x equals -3. The domain of exponential is always all real numbers. And then the range, it is above the asymptote at -3. For my inverse function, it is to the right of the asymptote at -3, so my domain is -3 to infinity. And then the range is all real numbers. Okay, so notice domain and range are also switched. In these next examples, instead of starting with exponential, we are going to start with log and end with exponential. Okay, for number 3, we're starting with a log function. First step, let's switch our x and y. And then we have to resolve for y. So to solve a logarithmic equation, we need to isolate the log. And so the -1, we need to add 1 to both sides. So x plus 1 equals log base 2 of y minus 3. Now that we've isolated the log, that says we're ready to convert. My base is 2 of x plus 1 to the x plus 1, since we're converting to exponential, equals the y minus 3. And so for my last step, we just need to add 3 to both sides, which gives me y equals 2 to the x plus 1, and then outside the exponent, plus 3. So 2 to the x plus 1 plus 3. So let's check our work. We started with a log base 2. We ended with an exponential base 2. We had a -3 inside. We have a +3 outside. We had a -1 outside, we have a +1 inside. So everything's checking out. Okay, and so if I'm listing the transformation for my original log function, we see this is right 3, down 1. Right 3, down 1. Okay, and so to graph a log function, you start with the vertical asymptote. So right 3 would put the asymptote at 3. And then we have an x-intercept that's 1 away, but this x-intercept has moved down 1. My next point is going to be a base of 2 from the asymptote, and then 4 away from the asymptote. Okay, and so our vertical asymptote is at x equals 3. The domain is to the right of the asymptote. The range is all real numbers. And that first critical point is at 4, -1. Okay, and so for -1, we also have 5, 0, and then we have 7, 1. Okay, so to graph my inverse function, this is exponential. That's been moved left 1, up 3. Left 1, up 3. Okay, and so since it's exponential, we start with the horizontal asymptote, up 3. And then my first critical point is the y-intercept, that's 1 away, but it has been shifted left 1. So I am going to move that to the -1 spot. Then my next point is 2 away, and then my next point would be 4 away. Okay. And then it is growing, and then approaching the asymptote. Okay, and so that first critical point is -1, 4. We see the asymptote is at y = 3. The domain is all real numbers all the time for exponential, forever left, forever right. And then the range is strictly above the asymptote at y = 3. So 3 to infinity. Notice everything is still reversed. And then if we were to write down our 3 points that we were able to graph using transformations, it would be -1, 4, 0, 5, and then 1, 7. All the points are flipped. And then if I graph my y = x line, I see that they are reflections across that axis. All right, now we are going to skip to proving inverses using composition. And so to use composition to prove inverses, you need to show that if we compose two functions and end up with x after everything cancels, they are inverses. You have to show both directions. And so in one direction, f is the outside function. In the other case, g is the outside function. Okay, so I'm going to start with number 2. Okay, and so I'm going to start with f being the outside function. And so if f is the outside function, I'm going to put g inside. Okay, and so your first step is to get the rule for f. Okay, so f says log of x plus 9, skip the x, plus 3. Leave a blank because that's where g of x is going to go. G of x is substituting x. So the entire g of x expression is going to be in the place of x. And so I have log, and then a plus 9, and then a plus 3 outside. And g of x is 10 to the x minus 3 minus 9. Now I call it the cancellation game, but you only get one cancellation per step. So the only thing that cancels immediately are these 9s. -9 plus 9 is 0. The 3's can't reach each other, and so that's the only move I have right now. So I have log 10 to the x minus 3, and then plus 3. Now for my next cancellation, the 3's still can't cancel yet. And so the only thing I can cancel now is noticing that I have log base 10 with an exponential base 10. The inverse property says those cancel each other out, leaving me with just that x minus 3. That's an inverse property of logs that we learned. Okay, and so finally the 3's can cancel. Okay, and so this does equal x, so these are inverses. So the end of proof symbol is like a little hashtag if you want to do that, but we're not actually done yet. We have to show the other direction technically, and where g is the outside function and f is the inside function. So now you get the rule for g, which is 10 to the x minus 3 and then a minus 9. And so instead of x, we're putting f of x right there. Okay, so in my next step, I'm going to write that expression for f of x. I'm going to leave some room. And then f of x is log of x plus 9. I don't have enough room. And then a plus 3 outside the log. Okay, now we're ready to cancel. One cancellation per step. So the only thing that can cancel right now are those 3's. Next, we have a exponential base 10 with a log base 10, which frees up that x plus 9. And lastly, the 9's can cancel. Okay, and so we get x going both directions. So let's do number 5. Okay, so f and g. We're trying to prove that these are inverses. So actually, let's do something that looks a little bit different. Let's do number 4, because this is very similar to what we just did. So let's do f and g. Okay. And so I'm going to start with f as my outside function, and g as my inside function. So the rule for f is 2 to the x over 3, but instead of x, I'm writing g of x. And so in my next step, I'm going to write the expression for g of x, which is log base 2 of 3x. Okay, and so now we're ready to cancel things. The 3's can't reach each other, but I have an exponential base 2 and a log base 2, which frees up that numerator of just 3x. And then now the 3's can cancel, which leave me with just x. So first direction is done. For the second direction, g is the outside function, and his rule is log base 2 of 3 times x. And so we're putting f of x where x used to be. So in my next step, I have log base 2 of 3 times whatever the rule for f of x was, which is 2 to the x over 3. 2 to the x over 3. Okay, so for my first cancellation, these 3's can actually cancel right off the bat. And then I see a log base 2 with an exponential base 2, which leaves me with just x. And so we proved both directions.